Mesdames et messieurs, honorable assistance, soyez les bienvenus. Ladies and gentlemen, welcome to all of you. I offer you a summary of my work entitled Optical Investigation of Porosilicon Layers developed for optoelectronics application. My work plan is introduction, methods, results and discussion, and conclusion. During the previous years, the porosilicon has received great attention from research due to its potential use in various industrial applications. However, very limited data of optoelectronics used in this field is available. It was reported that the photoluminescence of porosilicon has achieved a large-scale investigation, giving an explanation of the photoluminescence phenomenon by getting the optical properties of porous silicon. Moreover, some of the physical phenomena are still poorly understood due to the strong relationship between the porosilicon nanostructure and the preparing condition, including etching current density, etching time, and concentration of hydrogen fluoride. Herein, we need to investigate the optical parameters of porosilicon layer developed for optoelectronics application. In methods, the series of porosilicon samples were prepared using P-tip silicon substrate with substrate. The electrochemical cell presented in Figure 1 was made of Teflon, while the base plate was made of aluminium. The silicon wafer was mounted as the base plate, making a ring of silicon surface, which was exposed to the electrolysis. The porosilicon layers were performed using a controlled electrochemical etching method. The used electrolyte is a mixture solution of hydrofluoric acid and ethanol. The silicon wafers were ultrasonally cleaned in ethanol, acetone, and then tried by nitrogen before use for starting each experiment. The PL measurements were carried out by a solid laser and detected by a monochromator with a photomultiplier associated to the standard look-in technique. In result and discussion, all the porosilicon samples showed a visible PL at room temperature. In Figure 1 Figure 1 show the spectra of P-tip porosilicon samples that were obtained from different etching current density and etching time. The presented series in Figure 1 indicates similar variation of the PL intensities. However, a remarkable increase of the PL intensity ranged from 2.59 to 11.72 was noticed. The spectrum showed an improvement in the PL intensity as a function of etching current density. The Figure 1 presented the variation of porosity and integrate PL intensity according to the etching current. Meanwhile, the porosity of the integrate and density of PL increase a function of the current density. On the other hand, the PLM density of the porous layers increases as a function of etching time and current density. In the figure 4 and 5, the two enregistered curves using values obtained by ellipsometric techniques show that the thickness increases as function of etching time, meanwhile the porosity increasing as function of current density. Moreover, the integrate intensity PL increasing as function as thickness and porosity. Indeed, the absorption coefficient decreases with the increase in porosity current density values used as seen in the figure. This behavior is perhaps due to the decreasing of the amounts of the material responsible of the absorption. In figure 6 and 7, the calculate of the absorption coefficient allows us to plot the variation of the penetration factor with the porosity as a function of the porosity as a function of the current density. The figures show that this factor is an increasing function with the current density. The table 1 illustrated the different value obtained by in this experimental work. Finally, the conclusion is: in this study, porosilicon layers were prepared by electrochemical etching. The study of the variation of the thickness, porosity, reflective index, extension coefficient, absorption coefficient, the penetration factor, and the PL density as a function of current density was carried out. The variation of these parameters flow in increasing function except for the absorption coefficient, which decreases with the current density, will result that an agreement between the PL measurement presented by the PL integrate and density, along with the spectroscopic ellipsometry measurement presented by the thickness and the porosity of the porous layers obtained with etching time and varying current density. The absorption coefficient decreases with the increase in porosity, and the penetration factor of an increasing function with the current density. We also know that the data presented in this work is more promising, and the development of more promising in the development of layers for optoelectronics application. Thank you for your attention.